Any power system network is subjected to disturbances at any time and place. It is considered as one of the most stochastic systems ever seen by the human beings. To enhance the power system reliability, System Protection Scheme SPS is an effective tool for utilizing the power grid during rare contingencies. This method is often employed as secondary protection schemes. SPS is also termed as Special Protection Scheme. SPS is referred with different names by different users such as IEEE as System Integrity Protection Scheme SIPS, Remedial Action Scheme RAS. SPS is defined as a protection scheme that is designed to detect a particular system condition that is known to cause unusual stress to the power system and to take some type of predetermined action to counteract the observed condition in a controlled manner. During contingency condition, SPS can be used as a tool for maintaining overall satisfactory operation of the power system. SPS can be installed to maintain frequency deviation during post-contingency, and it is referred as frequency control SPS, or preventing the system from voltage collapse or overloading of thermal limit, and it is referred as network control SPS. Characteristic of SPS. SPSs are also known by other names depending on the originator, like special stability controls, dynamic security controls, contingency arming schemes, remedial action schemes, adaptive protection schemes, corrective action schemes, security enhancement schemes, etc. In these schemes, depending on the type of the problem, actions such as tripping of generators, intentional islanding of the system at predetermined locations, tripping of loads will be taken. The design of SPS should be properly coordinated with the existing protection system to maximum reliability. SPS are dynamic security control systems and are designed to control power system stability in case where the uncontrolled response is likely to be more damaging than the controlled response. SPS are devised by offline analysis as opposed to online real-time control. The reason behind being power system response is too fast to allow sequential control system logic. Involvement of a grid operator. Human intervention for corrective action should be kept to minimum compared to SCADA EMS. In certain cases, SPSs can be designed for the detection of system condition which results in overloading, voltage collapse leading to instability. This may require disconnection of single or multiple lines, generator tripping, increased HVDC power transfer capability, premeditated load shedding, or other actions which may cause problem of concern. SPS initiates corrective actions in mitigating the consequences of abnormal conditions without involving the isolation of faulted elements. SPS are primarily used where the protection is employed on the capability of power system instead on specific equipment protection. SPS are designed to take special action in response to the event disturbances detailed below, either individually or in combination. Transmission faults, cascading outage of lines, generator outages, sudden large load changeovers, HVDC pole blocking. The disturbance may cause following problems in power system. The solutions for the same is also detailed below. Frequency instability occurs when power system frequency varies beyond the operating limits. Corrective actions include generator tripping, rapid generation reduction through fast valving or water diversion, control of HVDC power transfer, load shedding, controlled opening of interconnection to neighboring systems to prevent spreading of disturbance, controlled islanding of local system into separate areas with matching generation and load, etc. Voltage instability is the failure of power system to maintain its steady acceptable voltages at all buses in the system. Remedial actions include changing of generation, automatic shunt switching, control of series compensation, blocking of tap changer position of transformers, under voltage load shedding, etc. Transient angular instability is the inability of the system to maintain synchronism. Preventive measures include breaking resistor, employing fax devices, reducing the mechanical power driving the generator, fast valving, disconnection of the generator, etc. SPS integrates large number of switching actions in a coordinated manner. One of the essential features of SPS design is that it should provide secure and reliable communication infrastructure for exchange of data amongst monitoring, controlling, and action devices. The action devices are required frequently for sending, receiving, filtering, analyzing the status and/or analog measurements. For this, it is necessary to have the following requirements: devices to support communication, compilation and analysis of data, ample bandwidth for meeting the time constraints of communication. It is reported that the available SPS are dedicated for a specific power systems. Dependability, security, selectivity and robustness are the basic criteria for which SPS is used. Design of SPS. The design of SPS process is divided into 5 steps. They are system study, solution development, design and implementation, commissioning, periodic testing, training and documentation. Classification of system states and contingencies. For purposes of analyzing power system security, it is first of all helpful to conceptually classify the system operating conditions into system states. Normal state. All system variables are within the normal range and no equipment is being overloaded. The system operates in a secure manner and is able to withstand predefined contingencies without violating any of the constraints. Alert state. If the system parameters are still within admissible ranges but the system does not anymore meet the criteria given for a secure state, i.e. it is no longer N-1 secure, the system is considered to be in an alert state or endangered state. Typically, the system reaches this state after a N-1 contingency. This state requires application of remedial actions without any delay in order to come back to the secure state, i.e. to comply with the N-1 rule. Emergency state. As consequence of contingencies beyond N-1, extreme or unforeseen contingencies, the individual variables that describe the overall system state could violate admissible operational limits and hence the system is considered to be in an emergency state, a disturbed state. A system being in an emergency state might not be able to fulfill its function with respect to consumer supply and power transits, but is not blacked out. However, there is the risk of system collapse mainly due to the loss of stability. Therefore, relevant actions must be taken immediately to bring back the system into acceptable conditions. Blackout state. A blackout state is characterized by almost total absence of voltage in a certain area of the transmission system as a consequence of tripping of generating units due to abnormal variation of voltage and/or frequency which occurred during the emergency state. Once the system enters the blackout state, the restoration plan shall be activated as soon as possible. Restoration. The restoration plan aims to reduce the duration of power system interruptions as consequence of blackouts by re-energizing the backbone transmission system as fast as possible, which allows gradual reconnection of generating units and, subsequently, supply to customers. Prompt and effective power system restoration is essential for the minimization of downtime and costs to the utility and its customers, which mount rapidly after a system blackout. To contain normal type of contingencies, the so-called N-1 rule is common practice in most large power systems worldwide. This concept is characterized by a predefined redundancy of power system elements which ensures a sufficient safety margin and robustness to operate the power system. Given that the transmission system loading is moderate, also exceptional type of contingencies can often be handled due to this robustness. As long as normal and exceptional type of contingencies are secured by means of redundancy and the normal power system control capabilities, e.g. PST, HVDC controls, fax controls, etc., no automatic protection measures to preserve the system integrity and to avoid the violation of operational limits are required. However,